So today it's our great pleasure to welcome Patrick Heimbach as our STEM speaker for this month. So Patrick is a computational oceanographer at the University of Texas at Austin. He's a professor at the Department of Geological Sciences, and he also has joint appointments in geophysics and computational engineering and sciences at UT Austin. And he's one of the leading experts on data assimilation of ocean data in particular. And he's, for example, active in the ECHO collaboration, which is one of the leading oceanographic data assimilation models. And he has also worked a lot on answering quantification in that context. So he's one of the leading experts in answering quantification for data assimilation systems, which is something that is actually very relevant and interesting for our group here and for statisticians and people who work with geophysical data in general. He earned his PhD from the Max Planck Institute of Meteorology in Germany, and also from the University of Hamburg. And today, indeed, he will be talking about this area of data assimilation. So the title of his talk is Augmenting a Sea of Data with Dynamics, the Global Ocean Parameter and State Estimation Problem. So with that, Patrick, please go ahead.
Well, thank you very much, Michael, for the very kind introduction and the invitation to speak in your seminar. So I should really emphasize that this is really work by a number of people, both in the group that here at UT Austin, CRIUS, notably Nora Lose, Anne Nguyen, Helen Piller, Tim Smith, but also really a large group of the ECHO consortium. And you have the links here if you wanted to see who is part of that group. I should emphasize this. So for today's talk, I would like to cover a number of things. So first of all, just framing sort of the problem as one of sparse data science. Of course, the popularity is at the moment in big data science, but I'd like to point out that for a lot of things we are still unfortunately a sparse data science, and I'd like to then explain a little bit on how we do data assimilation or inversion in the context of ECHO, and would really highlight here some of the important difference between using filter-based methods and smoother methods. And I will then go into one specific application that I thought could be of interest here, using Argo data for property analysis that I thought could be interesting here. Then also go into the use of gradients, which is of course what we at the heart of all of this, not just for optimization, but also for doing science like dynamical attribution. And today, actually, I'm going to talk less about uncertainty quantification. I touch upon it, but I've talked about this previously, and I thought maybe what I suggested before will be of much more interest. So first of all, I would like to drive home the point again that of course, we are in an age where we have a massive increase of satellite data and volumes. We have massive capabilities now to generate simulation-based data output that easily can go into the dozens or several hundreds of terabytes per simulation at very high eddy resolving and maybe even internal wave resolving simulation. But if we stick to the actual observations, oceanography really remains a sparse data problem, right? So this, what the figure here shows from Abraham et al. 2013, is that the observational coverage as a function of depth in the northern hemisphere at the top panel here, in the southern hemisphere as a function of years from 1950 to about 2010, we see that only since the beginning of the 2000s, we begin to have a fairly somewhat decent coverage of the upper 2000 meter. That, of course, is thanks to the advent of the Argo float data, looking better in the northern hemisphere, still not that good in the southern hemisphere. And let's keep in mind that the average depth of the ocean is actually 4 kilometers. So we're still not covering a large fraction of the full ocean depth water column. The right panel here shows you again this sort of global ocean volume covered by observations as a function of latitude. And you see that the the volume here that's shown in green is, of course, accentuated, as we know, in the southern hemisphere, but the observational coverage is still accentuated in the northern hemisphere. So there is that mismatch still. The observing system as a whole, like part of the global ocean observing system, is rather eclectic. We have satellite data, like here, sea surface temperature. We have the CTD data that we have been having for many decades, glider now becoming online, and then elephant seal data. All of these data have very different variables that they sample. They have different sampling patterns. They are regional. And the question is, how do we make sense of these different information sources? One is this Apache Global Ocean Observing System. But then we also have information from our dynamical understanding of the ocean circulation. That's the governing equations of motions, and how we can implement these governing equations of motion into computer models, which basically give us the information that we have from general circulation models. And the question is, can we optimally combine these two knowledge reservoirs, so theory and modeling on the one hand side, observation on the other hand side? Can we do so in a manner that we get really information that is useful for climate analysis? I'm emphasizing this, and you'll see a bit later in the talk why I'm really emphasizing this. But the bottom line is that in many cases we're seeking to detect small residual signals that are basically rising, or maybe not yet, involve the noise of climate variability. And can we provide measures of uncertainties with the estimates that we are seeking? And finally, can we use simulation, which is of course one thing that I'm heavily involved with, to inform efficient observing system strategies? Part of the answer to this is this ECHO, this estimating the circulation and climate of the ocean. It's been around for now 20 years. It's a multi-platform, multi-instrument synthesis effort that integrates ocean and marine ice observations with the equations of motions. And this project is now led out of JPL, PI Ichiro Fukumori, but it has several project partners, some formally tied, others more informally tied, that are shown in this picture. So what is ECHO about? So on the one hand side, we have a range of ocean dedicated or Earth observing dedicated satellites. Here at the top are the GRACE Gravity Recovery and Climate Experiment and its follow-on mission, measuring ocean bottom pressure changes since about 2003. We have this series of satellite altimeters since Topics Poseidon 1992 to present. And then we have a number of satellites measuring sea surface salinity now, and passive microwave satellites measuring things like sea surface temperature. On the other hand, we have in situ observations, such as the Argo profiling float data, CTD casts from earlier the WOS period, now the ghost ship period, XPT data, and then these marine mammals, elephant seals that are equipped with telemetry. And we'd like to basically take advantage of all of these very heterogeneous different types of observations and bring them into a dynamically consistent framework, which is represented by a model and the ocean general circulation model. And of course, the method to do this is broadly called data assimilation. And what is data assimilation? I'm using here two really nice quotes that I hardly could formulate any better. So one is from colleague Kaminsky et al. In 2015, who says that ideally all observational data streams are interpreted simultaneously with the process information provided by the model, which then leads to a consistent picture of the state of the system that balances all of the observational constraints and also taking into account all the respective uncertainty ranges. So that's that in a nutshell, or formulated differently by Steve Penny in a recent Frontier article. Data assimilation allows information provided from observations to be propagated in time and space to unobserved areas using the dynamical and physical constraints imposed by numerical models. So that's that. So I thought in order to earn the fact that I'm presenting here in a statistics seminar, I should actually couch ECHO the way how we do data assimilation within the problem of statistical or Bayesian inverse methods. And so that's what I'm going to do for you here, just to earn my credentials here in the seminar. It's probably for all of you 101, but I thought it could be useful. So again, so as you know, the textbook of Kai Pior and Salo 2005 formulates the problem is that the inverse problem is one of a statistical quest for information. On the one hand, we have observable and also unobservable quantities, and we're trying to solve the inverse problem because the unobservable or the unobserved quantities are the ones that are actually of primary interest. And we seek to extract information and assess uncertainty based on all available knowledge of the measurement process, of the models, and of prior information of unknowns. And so that really reflects again what I've shown data assimilation in the previous slide. And the solution of the inverse problem then in a statistical sense is of course one of a posterior probability density function of the unknowns. And so when we, to be more specific, we have the model, which in our case is the ocean general circulation model, represented by this general nonlinear operator curly L that propagates the state of the ocean from time t-1 to x at time t, subject to some parameters and boundary conditions, which are actually unknown, right? So you could think of this U vector containing everything that might be unknown about solving this problem. This could also be the initial condition, surface boundary condition, model parameters. You could, formally absorb all of this into this operator. On the other hand, we have observations at time t, and this curly E operator that projects the state, the simulated state at time t onto the observation. So sometimes it's called state to observable map operator, and then a residual noise vector here. And the statistical inference problem of the uncertain parameters U is one where we're seeking these posterior distribution of the uncertain parameters given the observations Y. And this, we're using Bayes' theorem to basically say we can obtain this posterior distribution by the product of the prior in the knowledge that we have on the unknowns, and then the likelihood of basically finding the observations given the unknown vector U. This in general, to solving this Bayesian problem in its generality for expensive forward models, such as general circulation models and high dimensional space of uncertain parameters, which could be 3D state of the initial condition, 3D model parameters, or even time evolving 2D surface fields, is of course extremely expensive, and so we need to make some assumptions. So the assumptions that we're making here, which makes the problem, of course, very simple from a statistics perspective, but it's still one problem that's still challenging computationally, but still, so our prior will be Gaussian. We can put in prior error covariance to impose smoothness on the solution. And then in the difference, this noise operator, difference between the predictable observables and the actual observations, which we also assume to be Gaussian. And then if I make just one more, just for practical reasons, I will just combine this nonlinear operator, which is the model and its projection onto the observed state into this map here of the observable to state observable map. Basically, what I'm now finding is this misfit here, and I can reformulate Bayes' theorem as basically one of the posterior as this in this much more simplest form, the Gaussian multidimensional Gaussian distribution with what you see here is already the misfit to the observations, and then a term representing the prior. And now this is where basically we're transitioning from a statistical inverse problem basically to the deterministic inversion, right? So under all of these assumptions, where also the posterior is assumed to be a Gaussian, we can now formulate this as a minimization problem where we seek the maximum or posterior point or the map point. So U map, that's basically those set of unknown parameters for which the simulated state fits the observations optimally, to within the prior or actually the observational uncertainty. And that is subject to some prior information on how much the parameters or the deviation of these parameters from the prior should deviate. And that, in a nutshell, is the echo parameter and state estimation problem. We can take this further, and of course, and then because we're now talking for the Gaussian posterior, we have the posterior error covariance, which we can formulate as a sum over the inverse of the prior error covariance, and then the Hessian midfit, basically, which is the second derivative of our misfit function with respect to the unknown. And I will get into this a little bit later. We can approximate this Hessian by the Gauss-Newton Hessian, which only involves sort of effectively first order derivatives, which is the tangent linear and the adjoint operator here. And we'll take advantage of this much later. So so let's go back to how we're solving the deterministic parameter and state estimation problem. So we have our model data misfit function subject to the prior information, and in order, so what we need to do, the optimization problem is one that we want to solve via gradient-based optimization. And since I've told you that this gradient lives in a very, very high dimensional parameter space, can 10 to the 6, 10 to the 7 dimensional, we need to find the gradient in a very efficient manner. And so the extension of this problem is the one of the Lagrange multiplier. We use the method of Lagrange multiplier, where we basically extend our misfit function to one where we seek to an extra term which requires the model equations to be satisfied exactly. And this is expressed by this extension of the misfit function to the Lagrangian with the Lagrange multiplier that we're introducing here. The points, the Lagrange multiplier methods basically assists in finding the stationary point in J leads to the set of normal equations. Finding the gradient of J with respect to the Lagrange multipliers recovers the model equations exactly. And then the derivation of the J with respect to the model state leads us to the adjoint equations. And the adjoint equations, what you see here, you begin to see they are the adjoint state is one that is time dependent. And what you begin to see is that this derivative, the model derivative with respect to this state, it's the Jacobian. The transpose of that Jacobian is the adjoint operator. So it's the transpose of the tangent linear operator, which maps the adjoint state or the dual state from t+1 onto the time t. And so if we, this is just to basically make this a bit more transparent. So any change at x at t+1 is related to the change, small changes in the state at t via this linearized, the tangent linear operator, where the transpose basically moves then from from the adjoint state at t+1 to t. And we can recover the entire chain from the final state to the initial state, because we seek to find the gradient or the sensitivity of this cost function with respect to, for example, initial condition is through applying the chain rule and the product rule of differentiation. And just to give you a flavor of what this looks like, so this would be the Lagrange multiplier at time 0, or dj dx0, which is basically the accumulation of all of the sensitivity at all times that are propagated back in time through to t equal to 0, and that are forced by specifics. So for example, at final time, if there's a non-zero term here, then this is propagated by this tangent linear model from final time to the initial time, or any specific perturbation that we are applying at time 1 that basically is just propagated once via one time step by the adjoint operator. Again, at any intermediate time, the adjoint operator, so mu at time t, basically consists of these 3 terms. So the one term is just all of these, as you can see, for the model data misfit problem, they are forced. You could think of any model data misfit as a forcing term. So if this was 0, then there would actually be nothing to propagate. So whenever the misfit is non-zero, you're forcing the adjoint model, and you're propagating this. For example, you have specifically at misfit at time t+1 that are propagated by that basically form mu t at time t, but that is superimposed on all of the misfits at time t+1 that have been propagated by one step with the adjoint model. The same with everything at t+2. And so you see how you're accumulating all of the sensitivity back in time via the adjoint operator. So this is a very powerful way in which you compute a gradient with respect to, for example, x at time 0 that accounts for all the misfits and all the uncertainties that occur at all times. So you're allowing yourselves to have a time resolved assimilation of the data in this manner. One more thing that I wanted to highlight here is that so far I've mainly talked about all the sensitivity or the gradient with respect to initial condition, but we can also expose that simultaneously we can compute the gradient with respect to all the uncertain model forcings that are given here by this term here. And the set of normal equations now changes in the sense that not only do you have this equation here, which we had in our previous example that I showed earlier, but we also have a normal equation when you take the derivative of the Lagrangian with respect to these uncertain controls, which again could be time varying surface boundary conditions or model parameters. And again, this adjoint model will simultaneously compute all of those gradients as well. So it's an extremely powerful and efficient method to compute these high-dimensional gradients.
Excuse me, can I have a question here?
Yeah.
Hi, I'm Martin. So I wonder if basically we can, if I understand correctly, that if the model was linear, this would be like an optimization interpretation of the Kalman filter. And in the case of nonlinear model, well, there's this thing called extended Kalman filter. So is that basically the same thing, just expressed from the optimization perspective?
That is correct. And in the linear case, they should be equivalent and they will converge to the same thing. I'm going to show you that one of the important differences between the filter, so the Kalman filter, and its working, and then smoother based methods, right? So there is you can augment the Kalman filter with what's called a Rauch-Striebel.
Right.
Yeah, I forgot the third name. I'm sorry, I'm just blanking here. But the smoother methods, I mean, some people call it the Kalman smoother, but strictly it is the RTS smoother. And then to basically obtain basically a smooth trajectory. And I'm actually going to go into this in a bit. But you're absolutely right. Yes, that's exactly right.
Okay, thanks.
Yeah, and the other, because it's become so popular, I wanted to make one very brief connection between variational data assimilation and machine learning, with the very strong correspondences that and you basically have a neural network which replaces your model. You have a loss function which you're seeking to optimize, as opposed to a cost function, and then you have weights in your, for example, neural network that you seek to train, right? In our case, these are the uncertain controls. And then you have a method called backpropagation, but from a mathematical conceptual framework, it is exactly the adjoint model. And in fact, you are using automatic differentiation, which I'll talk briefly in a bit about, to obtain this derivative between, so the gradient of your loss function with respect to the weights will be almost, conceptually exactly of how we obtain the gradient of our misfit function with respect to our initial condition and surface boundary condition. And this is, of course, different to a Kalman filter approach where you, in terms of proceeding. But, and I'm going to get to this. I just wanted to throw this up here just to make some compelling connections here between those two worlds. So Echo is learning from one of the most complete set of available observations and known physics using this Lagrange multiplier method. Very briefly, the underlying general circulation model that we're using is the MIT general circulation model. I'm not going to go into its distinct features. The one thing I would like to highlight is again that we need, of course, the adjoint of this model, which is of course a key ingredient. And for this, we're using what's called automatic or algorithmic differentiation. It's a computational technique, again, something that I don't want to get into. So just to tell you that handwriting the adjoint model can be almost as cumbersome as writing the nonlinear forward model itself. And so if you can avoid this, that would be great. And so automatic differentiation, of course, presumably would do this all for you. And so you can relax. Unfortunately, it is not as easy at all as that. A lot of effort went into writing and refactoring the MIT GCN in a way that actually allows it to play very well with AD tools, and also to generate code that is not just the formal derivative, but it's also computationally similarly efficient to the forward model itself. So a lot goes into this. I'm not going to go into this at all. Instead, what I'm talking about, and in fact, this comes back to your question a little bit, make a really important distinction between data assimilation as practice for numerical or for prediction in general, for example, numerical weather prediction, and then on the other hand, for reconstruction. So as we do in our community. So in numerical weather prediction, we're faced with a problem. We have relatively abundant data, sampling the 3D or the 4D, right, in time atmosphere. And what we are after is, a forecasting, a prediction problem. So what we want to have is we find the initial conditions which produce the best possible forecast. What's important to note here, in order to find those initial conditions, we don't necessarily have to conserve properties as we go from one forecast step to the next forecast step. And so an example of this filtering, and in fact of the Kalman filter here, is shown here in red. So you have a forecast, and at time it's this red curve here. You arrive at this black cross here, and at that time, new observations come in here in blue, this blue circle. And so this now you realize, your forecast doesn't fit the observations very well. And so you're basically doing an analysis which combines the background, so the information that you have at that time from the model, and the observation to produce a new, what's called an analyzed state. That's this point A. And the step that you're doing here, from this black cross here to this new red cross, is what's called an analysis increment. And of course, this is obtained via the Kalman gain. So that will basically provide you with the information, how much of a step should you be doing here to obtain this analysis increments. And it factors in the uncertainties in the observations, the uncertainties in the prior and the background, and that basically determines the size of the Kalman gain. And then you go on to your next forecast. You arrive again at point B, and again you see that your model has deviated from observations, and you want to basically obtain a new initial state that basically produces an optimal forecast for the next forecast period. And again, you have this analysis increment. It's important to note that each of these analysis increments violates conservation, right? So think about this as being the temperature field, the velocity field at this time, where you basically replace this by just a new 3D field at the same instantaneous time, and that violates your conservation laws at that point. So in that sense, any filtering problem is consistent over the forecast period, so from a red cross to the black cross, but not from the black cross to the red cross at the time of this analysis increment. In contrast, the smoothing problem, consists of what we not so much interested in a forecast, but we are interested in a reconstruction, right? So, and that's what we're interested in, is the blue curve here. And what we actually we don't want to violate these conservation laws at these distinct points, because part of the reconstruction is to understand what are the time varying changes. So the DDT of this property here, why is it doing this? What is its magnitude? How does it spatially vary? And can we make sense of it in terms of dynamics, for example, underlying Rossby wave, Kelvin wave propagation in the ocean, diabatic versus adiabatic processes, and so on. And so we're seeking to fulfill the model equations exactly over this entire period. That's why, and we think that for climate-related application of these reanalysis products or state estimates, trying to obey conservation laws exactly is important. And so the ECHO effort in that sense distinguishes, or at least separates itself from many other reanalysis products by being a smoother based product. So in blue curve, unlike other reanalysis products, which are basically built on these red sort of approaches. And as an example of showing you, that conserving property budgets, if you're not doing this, how this can be a problem. So this is a figure from a colleague that he's been trying, he tries to publish and is not successful, but I think it's a very instructive figure, hoping that he will be able to publish it at some point. This is the looking from a global ocean reanalysis product, where he's looking as a function of latitude, so from 80 south to 80 north. He is diagnosing all the components in the tendency equation for temperature. So basically you have left-hand side is the total, the TDT, so the change of temperature over time is, and then on the right-hand side are all the contributions. So this can be an example here in black curve. This is the resolved advection, neutral diffusion, vertical diffusion, and all of these different terms basically contribute to the right-hand side. Forcing is also one of them, surface forcing, of course. And what you see here, so this is a function of latitude. This is a mean taken over a certain period where all those terms have been gathered. What you see here is, so as we might expect, the resolved advection is the dominant term, that's the black curve, but the second most important term, and in fact almost tracing the resolved advection term, is the analysis increment. That's this gray dashed curve here. And so what that means is that the second dominant term in your tendency equation for the tracer, in this case the temperature, is an unphysical term in your equation of motion. So, which I think makes it quite difficult if you begin to now interpret these reanalysis products without basically taking into account what for example, the analysis increments are actually doing to the solution. An example or a hint of how this can, go wrong at the global scale is that in the atmosphere here. So if you take the net air-sea heat fluxes integrated over the ocean, and you take this sort of the annual mean, and then you look at this for several decades. These are the net imbalances in the net air-sea heat fluxes from different reanalysis. So it's anywhere between here -20 and even +30 watts per meter square. And of course, we know the number, we have a good estimate of what the number should be. Namely, it should be somewhere below 1 watts per meter square. In our latest estimate, on the order of, let's say, 0.5 watt per meter square. But this is kind of the level that we're looking at. And all of these reanalysis products are in one way or another way, way out of balance. And so, which basically means they cannot be used in some ways for, looking at global trends in net air-sea heat fluxes over long periods of time, right? So, and it's clear that the reason why that is the case is exactly that they violate properties through these analysis increments. So just this one really important distinguishing feature between ECHO as a smoother-based reanalysis product and then filter-based methods. I'd like to switch gear here and go into one application, science application that we can do with ECHO, which I thought could be of quite of interest to this group, your group, working with Argo data. It's based on other people's work. A former student at Woods Hole, Gwyn Evans, and at MIT, Gaël Forget, looking at the dynamics and variability of North Atlantic mode water formation, or water masses, these mode waters sometimes called 18-degree water masses. They arise here to the south of the Gulf Stream in this area here. You see here an anomalous vertical transport. Here, this would be in Swerdrup per meter square. And basically, I am not going to go into the detailed calculation, but what you have is you have as a function of the season. So you have here from over the month from January, February, March, and so on. You have basically here you have isopycnals here. You have good stratification throughout the summer months. And then as the fall and winter comes, you have heat loss at the surface these isopycnal tilt up, and you basically have a loss of stratification at the column, and you have this formation at depth here, 300-meter depth, of what are then called mode waters in these regions. And the question is, first of all, what exactly is the origin of those mode waters? How much of it has actually been produced through these diathermal processes, so through diabatically, through thermal forcing, as opposed to processes of lateral advection by the circulation. So this is, of course, an important science problem. And clearly, Argo float data that we have now since the mid-2000s can be very powerful observational constraints on basically capturing those mode water formation over time. And indeed, so this is what Gwyn Evans and colleagues have been doing. On the left-hand side, so this is a little bit of a busy plot. See if I can walk you through this. This is based on Argo data, on the grid Argo product, Romick and Giltz in 2009, from 2004 to 2012. This is the temperature classes, and what is shown here is the volumetric, so volume anomalies in these temperature classes, right? And so the 18-degree mode water is something that you see basically here, and you see these water masses residing, at 18 degree, and you see how the these anomalous, basically a seasonal cycle in the way that I've explained before, of basically those waters being produced. So again, keep in mind, so this warm colors is just volume anomalies of certain of these temperature classes that basically suggest basically a production rate over the year at repeating year. This volume anomaly, so we have the same calculation here of such a volume anomaly of for production of 18-degree mode water here, derived from the ECHO version 4 product, which, and those look fairly compelling. They look fairly similar. There's other ways in which they differ, but we can, I think, to a good first order, they look quite similar. You see certain events here, sort of larger than average volumes here in the early, so more like 2005, and then less than average here towards the 2010 period. So we want to know, so we have these volume anomalies, and now we want to say, okay, how do these volume classes change in time? So we want to take the dV/dt, the time derivative of these estimates. And what they find is that trying to do this with the gridded Argo product is almost impossible. And the reason, there's a number of reasons why you can think of why this might be impossible. Basically, the subsampling and aliasing of the individual Argo data is probably one of the strongest contributor to this. So the answer is, even if the Argo and Argo data and the products are very good, what we're sometimes interested in is time changes, or very detailed, budget calculations that involve time changes, that involve, and gradients and so on. Once you get into the detail of those calculations, even these data become limited. You can do a similar calculation based on the diathermal transformation rates, based on some theory, Weyland analysis, which you can perform if you have available RC fluxes. And this is one that's been diagnosed using the NCEP RC fluxes and the Reynolds SST. And basically, this shows you the DDT term diagnosed from just the RC fluxes. This is the bottom panel. On the right are exact same calculations again, now using just the dV/dt calculation with the ECHO product. And here you can actually provide, obtain meaningful values. And the reason why you can do this is because you can actually diagnose. The model basically provide the solution to the governing equations of motions, actually ensures that the state that you're estimating fulfills some of these time derivative properties and relationships. So the point here being is that you can produce such dV/dt analysis with this dynamically consistent product. Here is another of such, again, inferred diathermal transformation using a slightly different RC flux product. That's the RC flux product that comes with the ECHO product. It looks quite similar to the one that's been obtained with the NCEP product, slightly different, but And again, you see these specific events that occur and that have been of interest to this paper, the 2010 event here with the at low degree. And again, the question that the paper then goes on to ask the question, how much of this is diabatic and how much of it is adiabatic contribution. Again, the adiabatic contribution being through changes in transport in and out of the box that the group was analyzing, and basically finding some interesting decomposition between those two, which I'm not going to go into it for detail. Just wanted to show you the power of of a state estimate that is dynamically consistent compared to just using the raw observational product as such. I wanted to go into another piece of analysis, and that is sort of called beyond optimization. And the point here is the use of the gradient information or of the adjoint, not just for optimization or for data assimilation per se, but for scientific analysis, in particular, what we call dynamical attribution of certain quantities. And the context here is that of, as an example, here the dynamical attribution of South Atlantic Ocean circulation changes. This is here shown here. The right panel here is a sort of a schematic of sort of the large scale circulation here, warm surface waters basically entering the South Atlantic through the Agulhas leakage here, and then basically feeding, ultimately the sort of the one branch of the Atlantic meridian overturning circulation. The efforts to measure this transport here at 34 South via this Samba mooring array, and the left panel here, forgot to actually add the label here by Lisa Biel et al. In the paper, basically just showing the wider context of the large scale circulation between the Atlantic and the Indian Ocean. And so what we're interested in here is the transport here at 34 South, it varies, of course, of seasonal timescales, but it also varies on interannual timescales. And we are interested in what are the drivers of this transport anomaly. And to ask the question, basically our quantity of interest now, our sort of previously was our cost function J, is now no longer, is not a model data misfit function, but it's basically just a transport anomaly at 34 South. And we're interested in how is this quantity of interest, transport anomaly, sensitive to all of the different surface forcing fields, and also at all times, so at all time lags. And again, the adjoint that's the figure that I've showed before, enables us to actually propagate those sensitivity back in time. So through the adjoint operator, that's this L transpose here from, let's say, if we evaluated our transport anomaly at a final time, we can now ask the question, how is the sensitive to the state of the model at earlier times, propagated by the adjoint operator, and then of course propagated from that to the surface forcing anomalies. This is work by Tim Smith here, who basically calculated sort of these adjoint sensitivity back in time. What we see here, so this is the sensitivity of this transport anomaly to the changes in the zonal wind stress back in time. And what you see, some of the features that you see are interpretable because we're looking at the adjoint state. These are basically time reversed Rossby wave and Kelvin wave propagation that are basically being triggered by surface zonal wind stress anomalies at short times. Something that, if you see at short times, you also see effects of short-term Ekman transport here near just the 34 South arrays, and so very powerful way of trying to make sense of this space-time sensitivity. This can be taken further, and you can use the sensitivity maps as a sensitivity kernel for a Green's function-based reconstruction of your transport anomaly at 34 South. And that's exactly something that Tim has done. And so he looks at the transport anomaly as a function of year. So he basically removed the annual cycle. And so this focusing on the interannual components. And what he says, at each individual year, so in one year, so the impact will be very local. So the major contribution will be the wind stress locally between 30 and 40 south. That would be something around, say, 2001. But then there will be other years, for example, here, 2005 or so, where the subtropical North Atlantic actually played somewhat of a role. There will be years when you have to probably, especially here in the 1998, 99 year, where you have sort of a teleconnection between the tropical Pacific and wind stress changes over the tropical Pacific influencing the area. So this is a very powerful way on how we can dynamically attribute changes in the transport array to, for example, surface forcings at back in time over a certain period of time. I'm just going to rush through sort of the last piece of analysis is the or application is the uncertainty quantification, which we can do using now the second derivative. So the tangent linear and adjoint, these were this first derivative of our misfit function with respect to the unknowns. And then taking this a step further, basically is this Hessian-based analysis. I'm just recall, for always important to keep in mind. So when we talk about uncertainty quantification in the context of data assimilation, the different uses and purposes. One is for parameter estimation or calibration. Another one, which is mostly of our interest, is for state estimation or reconstruction. So that's an interpolation problem, or for forecast initialization, which is basically you try to quantify the uncertainty in the forecast in this extrapolation. And of course, the different sources in the context are in the observations, both in their observational, just the instrument error, but also potentially in the context of data assimilation representation errors. The assimilation scheme itself comes with uncertainties in the way on the approximations that we use, either in the ones, for example, for the adjoint, but also in any of the Kalman filter, which always also has to make certain types of approximations. The underlying model used for interpolation has parametric uncertainties, the boundary conditions, and so all of those we would like to capture. And of course, that comes back to how we integrate all of these different uncertainties into this current framework. And the answer, again, this brings me back, and I've shown this slide before, is basically, at least in, when we, with the Gaussian, the posterior covariance that we obtain along with the map point. So is one where we have the Hessian misfit at the map point, combined with the inverse of the prior, and then the inverse of that. And then again, we can calculate via the adjoint and the tangent linear operator based on the inverse error covariance. We can compute this component, and then we can see how to what extent these observations actually help to reduce the prior uncertainty. And that is shown sort of emblematic in this figure here, where you have the Hessian basically tell us something about curvature, right? In one direction in which the curvature is large means that the observations constrain the uncertain direction of the parameter very well. And in another direction in which the curvature is very low means that the observations have almost no impact on constraining that parameter. That's kind of the interpretation of the Hessian, and then we can begin to do an eigendecomposition of the Hessian. We're basically looking at the principal curvature, if you like, of the Hessian, and compute basically to tell us something about the directions or those parameters in parameter space that are best constrained by the observations, and then of course also the null space of parameters that are not very well constrained. This leads to, after some algebra, and we can make a low rank eigendecomposition of this posterior that actually makes the problem tractable. So, and leads us to both an inference of the directions in parameter space that are best constrained and the corresponding eigenvalues corresponding to those directions, and then a measure of the posterior and how much the observations are basically helping to reduce the prior information. And using this now for uncertainty quantification and observing system design is something that I don't have time for, but excitingly, just yesterday or 2 days ago, the paper by Nora Lose came out, which basically describes the use of this Hessian uncertainty quantification approach for observing system design, basically asking the question, what observation types and placements have the biggest impact on a quantity of interest for which I would like to reduce my uncertainty. And so I'm finishing here with basically just this very nice sort of figure here that basically has to sort of diagrammatically, schematically say, bringing together observations, theory, and computational models within this inverse framework to try to improve our understanding and for decision making. I'm not going to leave you with this, but rather with this, which is probably very, very appropriate for ECHO is trying to do. And I'll leave you with that and be happy to take questions. Oops, sorry.
Cool. Thank you very much. This was super interesting. So let's see if we have any questions here. We have some clapping. Let's see, clapping. If anybody has a question, feel free to you can either use the raise hand button or you can put it on the chat box, or you can probably just unmute and ask the question. So if anybody has a question, feel free to go ahead.
I could start us off.
Yeah, go ahead.
Patrick, thanks for the great talk. I really enjoyed it. I wanted to ask about when you were doing this automatic differentiation process on the general circulation model. How did you actually go about doing that? Was that a particularly hard part of this research?
Yeah, so that's a great question. In fact, it is fair to say that the person who developed the AD tool almost alongside with the development of the MIT GCM. So the automatic differentiation, I think, for a very complex model, especially for legacy code, is kind of dishonest. Sounds a bit mean, but it's really not capturing this. So there's AD automatic differentiation comes in two parts, right? One is called the forward mode, by which you just generate the tangent linear model. And that part is actually straightforward, and many AD tools are actually fairly good at doing this. Where it gets really messy and complicated is when you go into the reverse mode, which is what you want. You want the adjoint because it's a mapping from R1 to Rn. And so that means one adjoint integration gives you the gradient with respect to all inputs, so the n dimension, as opposed to the tangent linear, which is a mapping from Rn to R1, which would have to run n times in order to then reassemble the gradient. So the AD tool, so it's been a very it's taken a long time, and so we wrote the MIT GCM has been to some extent written with AD in mind. So we had been careful not to use features of that, for example, the AD tool would not be able to digest, or something like go-to statements. So you should never use go-to statements anyways. But in this specific case, this is particularly bad because you have to think about reversing the flow of information jumping, from a loop, for example, somewhere else in the code. It's just makes things extremely hard. So to generate the reverse mode of AD, so the adjoint takes both, you have to be compliant with what the AD tool can do. It's a highly specialized tool. It's not a big community, so it's not that well developed. And you have to make it in a way to keep the efficiency, right? So that the adjoint model also remains efficient. I can talk, I can spend another hour talking about this, but the bottom line is it takes quite some effort. But the thing is that once you are, because we have been successful, we can also repurpose very flexibly the MIT GCM to various different types of application. And so you see now we can repurpose it for regional, as data like the Southern Ocean State Estimate. We can repurpose it for coupling it to, we have a couple physical biogeochemical model, an ocean sea ice model. And once you have the system in place, it is really easy to reconfigure and to basically to build on this to really flexibly create a whole number of experiments. So this is the real power of the algorithmic differentiation. Getting it into place, getting the model to work well with the AD tool takes time and effort, and also willingness to avoid certain modeling structures. But if you have it in place, there is many things you can do, and you can recompile the model, you can configure, you can use all of the ways in how you can configure the model, and you can take advantage of AD to then generate you the adjoint code that is the suitable one for the problem that you are configuring. So that's, and one thing I should say, we have been, so the AD tool that we have been working with and still for a while is a commercial tool, TAF. We have been working on an open source tool because we were kind of frustrated that the wider community isn't able to use this, this feature, and because they have to buy a license. OpenAD we have been able to come some way, but it's hit sort of a little bit of a roadblock for some reason I don't want to go into. We're working with the OpenAD people. We're actually now working on another tool called Tapenade coming out of France. And that code has recently been open sourced completely. So that means that both the AD tool itself is open source, and it can be used, of course, in an open source manner to generate your adjoint code. And we're beginning to work on this and see whether we can generate an adjoint of the MIT GCM using Tapenade. Yeah, sorry, long story, but I could get much longer.
No, thank you for that. That was great. Thank you.
Cool. So let me ask one question. I want to ask about the answering quantification part, and I noticed that you're using the Hessian for the uncertainties. I was wondering, so there's another data estimation problem that we have been recently looking at, which is this carbon flux inversion problem, where you use satellite data to invert for the land air carbon fluxes. And in that area, they actually don't use the Hessians. They use a rather different type of a technique, although they're still aiming to get kind of the posterior covariances. And when we've been talking to them, like they say, they have certain reasons why they don't like the Hessian. I believe part of the reason is that you would end up with this like gigantic matrix, which is difficult to compute, and they have kind of computational issues in doing that. They have storage issues and so forth. So I'm wondering, like, can you say a bit more about, like, how common is it to use the Hessian versus potentially some other techniques? What are the pros and cons between the Hessian approach and other techniques? And why in your application you're able to actually use the Hessian, while in some other applications they seem to be sort of pretty sort of determined that it's sort of very difficult for them to do. So why in this case it's doable, while in some other case it's not so doable?
Yeah, I mean, that's a great question, and I should state that we are really just getting into this, so I shouldn't oversell that we are sort of using this in a sort of operational production manner, but we're basically developing this Hessian framework now. The reason why we can use it is because it relies on derivative information, and especially if we can rely on just using the Gauss-Newton approximation, we have which requires the adjoint and the tangent linear model, both of which we have and we can generate. And so we have an ability to compute the Hessian to begin with, which almost nobody has, right? Because it would be, I mean, at least in a way, there's other approximate ways of computing the Hessian, but in using it in this Gauss-Newton way. Now, the second thing though is when I say we can compute the Hessian, that's actually not true, right? Because it's if it's a 10 by 6, by 10 to the 6 by 10 to the 6, we're not actually computing the Hessian in that sense. What we can do, we can compute very efficiently Hessian vector products, right? So that's something we can use very efficiently. And so now we can use these approaches that we can, application of a Hessian on a vector, we can begin to use method like the Lanczos method. And on the one hand side, and we can use this reduced rank methods to basically reduce first of all, reduce the dimensionality of the space, and then using Lanczos methods to be able to actually compute sort of, the first n eigenvectors and eigenvalues of that Hessian. And what's been found is that the eigenvalue spectrum in many of the application actually drops rather rapidly. So even in high dimensional problems, it's been evidenced in quite a few applications that as you go sort of, if you compute the first 50 eigenvectors and eigenvalues, the eigenvalue spectrum drops by maybe even orders of magnitude, which gives you at least a good reasoning to why, what you're computing is actually useful. At least you're getting sort of the leading, what are the most important constraints on observations on the problem. But of course, you're still left with a very high dimensional null space, right? So that you're basically not computing. And then finally, what there for, when you bring in multiple observations, and so then things that we have not yet looked at in more detail are randomized methods, right? So then within the Lanczos algorithm, also to look at randomized methods to actually solve for when in the observation design problem, when you work with many sort of multiple observations and actually looking at the observation impact. And this is something that we have not started with. I know that another group, that's the only other group that actually works in that space on short and regional timescale, the ROMS group, Andy Moore at UC Santa Cruz. So they have been applying this. I do know, though, that from a carbon cycle data assimilation system, there is a group in Europe that actually has been, as far as I know, using both adjoint and Hessian methods for also uncertainty quantification. That's I can send you the reference. People involved are, at least a while ago, Marco Scholze, who I think was in Sweden, Thomas Kaminski in Germany. And so they've been using that's called the CCDAS, Carbon Cycle Data Assimilation System, where they are actually, it's more on the land, sort of on a coupled land, maybe vegetation model. And they are ones that I think are using Hessian-based methods for uncertainty quantification. So yeah, but the main reason is, again, we have the ability by virtue of having the adjoint. We certainly have to avoid computing the full Hessian, but working with Hessian vector products and then basically using Lanczos methods. Those are some of the answers.
Yeah, cool. Thank you very much. Yeah, if you have the reference, that would be really interesting. I will send it to you to have a look.
Yeah.
Okay, so let me see if you have any other questions here. So does anybody else have any questions in mind? I think we have one hand up. Mike, please go ahead.
Yeah. Hey, Patrick, that was a really great presentation. So actually, I'm the one working with Mikhail on kind of this carbon flux inversion problem, and yeah, we've been thinking about how to get this posterior covariance matrix. And I'm curious, when you're just taking like R of the eigenvalues in that matrix, do you end up getting kind of what I'll call small number problems, where if the spectrum is decomposing very quickly, that if you're not using those like very small ones, that it can create instabilities or something like that. This isn't particularly well formed, but I'm just curious, if I'm missing out on those very small eigenvalues, you actually can lose quite a bit in terms of that covariance matrix.
Well, that's a great problem, and the answer is it's something I don't have a good answer. It's something that we're also still learning on what it all means and why it works. And maybe the related problem is one that I like to sometimes call out is in the context of singular vector decomposition, where in the numerical models, right? So where also sometimes you get, if you formulate it in the context of numerical weather prediction, where you have these small perturbations that amplify, and they're coming from non-normal amplification, so the non-normal superposition of modes that are small at initial time. If you try to find them as initial condition perturbations, you don't actually see them. They would certainly not be visible in like an UOF decomposition. They're small features, but then they amplify maximally over a certain period of finite time. And that's exactly an example that you are, I think, maybe have in mind, even where it's at least in that sense, it's a small perturbation, but it leads to a maximum amplification of whatever norm you provide with it over a finite time. And it's been, and so for the uncertainty quantification, I don't know the answer. So we're really learning about this, and all I can do is I can give you sort of what we've been doing with it so far, and then also I know that some people in the iSheet modeling community have also been looking at this and looking at you know, the uncertainty, the posterior uncertainty when you do inference from basal properties to look at ice flow, right? It's an even bigger problem in some sense than oceanography. The ice flow is heavily dependent on the basal condition. We don't know it, so we invert for it. But then, what are the posterior uncertainties? And again, they find this very strong in the basically uncertainty space. This very sharp decay in the eigenspectrum. And it's a great question, and I don't know, maybe in 10 years, if I manage to understand more what's going on, or yeah, I can tell you, but I think it's a great question.
Great, yeah, and I mean, it seems very non-trivial, so I'm just curious if you had, you know, if there's something obvious that I was missing, but thank you.
Cool. So, so since we are starting to be a little bit over time here, we probably should kind of finish the official part here. I don't know if Patrick has time to stay around, you know, if you have any extra questions, but let me just, I'll go ahead and stop the recording here.